the birthplace of tornadoes. Supercell thunderstorms. Before we dive into RFDs, let's start with the environment that creates them. Supercell thunderstorms. These are not your average storms. Supercells are large, rotating thunderstorms that can last for hours and produce the most violent tornadoes on Earth. At the core of a supercell is a deep, rotating column of air called a mesocyclone. This rotation begins high in the atmosphere, where strong wind shear, changes in wind speed and direction with height, causes air to start spinning horizontally. Then, powerful updrafts tilt that rotation into a vertical position. When you combine warm, moist air rising rapidly with intense rotation, you get a perfect setup for a tornado. What exactly is an RFD? The rear flank downdraft, or RFD, is a region of sinking air found on the backside of a supercell thunderstorm, usually near the area where a tornado forms. Picture a thunderstorm as a giant engine. Warm air rises on one side, cool air sinks on the other. The RFD is that sinking air, cold, heavy, and fast-moving, wrapping around the back of the storm like a spinning curtain. This downdraft happens when rain and hail fall through the storm's updraft, evaporating as they drop. That evaporation cools the air rapidly, making it denser than its surroundings. As this cold air rushes downward, it accelerates toward the ground. When it hits the surface, it spreads out in all directions, but some of it curls back toward the storm's center. How the RFD interacts with the updraft. One of the most fascinating things about RFDs is how they interact with the storm's updraft, the part of the storm pulling air upward. The RFD wraps around the updraft like a hook, bringing with it cooler, drier air from outside the storm. As it wraps around the mesocyclone, it helps tighten the rotation near the ground. Think of it like an ice skater spinning faster when they pull their arms in. The RFD does something similar for the storm's rotation. It compresses and concentrates the spin, helping the funnel cloud stretch downward toward the ground. Without the RFD's interaction, many storms would never produce a tornado at all. It's the bridge between the rotation high in the atmosphere and the tornado we see on the surface. The role of temperature and moisture. One of the reasons RFDs are so unpredictable is because their temperature and moisture levels can determine whether a tornado will form or fail. If the RFD air is too cold and dense, it can choke off the storm's updraft, cutting the tornado off before it starts. But if the RFD is just slightly cooler than the surrounding air, it can actually enhance the updraft, feeding more warm, moist air into the storm and making a tornado more likely. Meteorologists call this balance buoyancy. A buoyant RFD, one that isn't too cold, creates the perfect blend of rising and sinking air that allows rotation to intensify near the ground. In other words, the difference of just a few degrees in air temperature can decide whether a storm spins up a weak funnel or an EF5 monster. Visual clues of the RFD in action. You can actually spot signs of an RFD in real storm footage, even before a tornado forms. When storm chasers talk about a clear slot, that's often the visual signature of the RFD. It appears as a bright, rain-free area wrapping around the base of the storm, just behind the wall cloud. The clear slot marks the edge of the downdraft where the air has sunk and dried out, creating a visual gap in the clouds. Shortly after the clear slot appears, you'll often see the wall cloud tightening, rotating faster, and sometimes dropping a funnel. That's the RFD doing its work, wrapping around, compressing rotation, and focusing it near the ground. The physical force of the RFD. To understand how powerful an RFD can be, consider that it's not just a gentle downdraft. It's a blast of air that can reach speeds of 100 miles per hour, 160 kilometers per hour, or more as it slams into the surface. This sudden burst can push objects, lift debris, and create powerful gust fronts that move outward from the storm. When it hits the ground, this downdraft spreads out and curves back toward the storm's core, dragging rotation down from above. The collision between this inflow of cool air and the storm's warm updraft zone becomes the birthplace of the tornado. It's like the RFD gives the storm that final shove it needs to spin up the funnel cloud. The moment of tornado genesis. Tornado formation, what scientists call tornado genesis, is often triggered at the boundary between the RFD and the main updraft. At that point, you have air rotating horizontally, vertically, and diagonally, all colliding in one small area. The balance of warm, rising air and cold, sinking air causes the rotation to stretch vertically, As it stretches, it speeds up dramatically. Eventually, that rotation tightens enough for a visible funnel to form and touch the ground. Interestingly, the RFD doesn't just help create the tornado. It can also control how strong it becomes and how long it lasts. If the RFD continues feeding the tornado with fresh inflow, the funnel can grow and strengthen. But if the RFD cuts off the storm's warm air supply, the tornado will quickly weaken and die. RFDs and tornado life cycle. The RFD plays a part in almost every phase of a tornado's life, from birth to death. At first, it wraps around and tightens the rotation. As the tornado matures, the RFD continues to supply cold air, shaping the storm's inflow pattern. Eventually, though, the same process that created the tornado can destroy it. As more cold air fills the storm's base, it can choke off the warm, moist air feeding the funnel. The tornado begins to rope out, stretching thin before finally dissipating. This balance between the RFD's power and the storm's inflow is what makes tornado lifespans so unpredictable. A single shift in the RFD's temperature or direction can decide whether a tornado lasts 2 minutes or 20. Why scientists study RFDs so closely? For meteorologists, understanding RFDs is key to improving tornado prediction. While radar can detect storm rotation high in the atmosphere, it still struggles to forecast whether that rotation will reach the ground. The RFD is the missing link. It's what turns rotation aloft into a surface tornado. Researchers deploy mobile radar units and specialized probes near supercells to measure temperature, humidity, and wind speeds inside RFDs. They've discovered that even tiny changes in RFD behavior can dramatically alter a storm's potential. Some experiments, like Vortex 2, have focused entirely on RFDs to figure out how to distinguish between tornadic and non-tornadic storms. RFDs, the hidden power behind tornadoes. In the end, RFDs are the unsung heroes, and sometimes the villains, of severe weather. They don't get the same attention as the visible funnel cloud, but without them, tornadoes as we know them probably wouldn't exist. The RFD is the spark that triggers chaos, the invisible hand that sculpts nature's most violent storms. Understanding RFDs isn't just about science. It's about saving lives. Every new insight helps meteorologists issue better warnings, giving people those precious extra minutes to take shelter. So the next time you see storm footage with that eerie, clear slot wrapping around a dark, rotating cloud base, know that you're watching the RFD at work, the final step before nature unleashes one of its most powerful forces.